Hello friends, in this session we will go through the challenges which we can encounter in space. There are several challenges that we need to overcome to have a successful space mission and meaningful space exploration. As you know, Sputnik was the first artificial Earth satellite which was launched into an elliptical low Earth orbit by the Soviet Union on 4th of October 1957 as part of their space program. By today's standards, Sputnik was a humble satellite with a weight of 85 kilos and powered by a 1 watt battery. It sent a radio signal back to Earth for just 3 weeks. Nonetheless, it gave information about some of the fundamental operations which became the stepping stone for launching satellites and into various orbits with increasing weights. Once we reached space, we realized there are more challenges for exploring space than we have theorized before. First and foremost is gravity, then the consequences of great distances that have to be traversed, then the challenges posed by space debris and the ways in which we should navigate around them in space. Also, in case of human space missions, there are other effects such as radiation, microgravity, etc. Human beings who travel to space will have to change their lifestyle and will also have to withstand psychological effects of long periods of stay in space. We shall now see each of these challenges in detail. Gravity, as you know, has its own advantages and disadvantages. It keeps us rooted to Earth. But when we have to explore space, we have to overcome this. Or we have to escape the gravity to explore space. As stated in Newton's universal law of gravitation, every object attracts every other object in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So suppose you want to explore space, you have to come out of this gravitational force exerted by Earth by traveling at roughly 11 kilometers a second, that is 40,000 kilometers an hour, to escape this pull. A rocket burns tons of fuel just to cross the Kármán line, the imaginary line at roughly 100 kilometers above Earth's mean sea level, which separates Earth's atmosphere and outer space. The rocket shown here, Saturn V, burned 20 tons of liquid oxygen and kerosene to lift the Apollo spacecraft from the surface of the Earth. So to achieve that kind of velocity, you have the weight pulling you down towards the Earth and the thrust which is required to push the weight up to so that you can achieve the desired velocity. That means there are some limitations on the capabilities of building a rocket. For example, if you design a rocket of 400 tons, what is the amount of useful payload you can have on the rocket so that you will be able to escape from Earth and also do some meaningful science with it? The amount of propellant which is required forms the bulk of the weight. The material with which the rocket structure has to be built takes the next most amount of weight. So the remaining weight for the useful payload of satellite is very minimal. For example, Saturn V rocket generated 3.5 million kilograms of thrust to counter the rocket's 2.8 million kilograms of weight. such that the net force will push the rocket upwards. We want to have more payload and more useful instruments in space. But to push that kind of weight to space, you require huge amount of propellant. On your screen, you see the International Space Station. It is a multinational collaborative project involving 5 countries: the USA, Russia, Japan, Europe, and Canada. This station is the largest structure man has ever built in space, and it serves as a microgravity and space environment research lab. It weighs about 420 tons and is as big as a standard football field. It took more than 40 launches involving rockets such as Saturn V, the Space Shuttle, Soyuz, and Proton to assemble the International Space Station. The next challenge in space is that it is a really dangerous minefield. Once we enter the space, it is a minefield of objects waiting to collide. Near Earth objects, or NEOs, like asteroids, comets, and meteoroids, whose orbit intersects Earth's orbit, and space debris or space junk from space exploration missions pose a collision danger. Millions of asteroids are accumulated between the Mars and Jupiter called the asteroid belt. Some of them may get reflected and may become big bullets coming towards Earth. In fact, there is a theory which states that Moon was formed due to bombardment by a huge asteroid. Earth got split into two, and that is how we had the birth of the Moon. The Moon even today is moving away from Earth, which means some millions of years ago, the Moon was very close, such that solar and lunar eclipses used to happen very frequently. But luckily, these asteroids and small rocket parts which get detached come charging into the Earth's atmosphere and get burnt out. Apart from asteroids, there are spent stages of a rocket launch, like the first stage, second stage. They also act like satellites revolving around the Earth, except that they do nothing. Eventually, they may enter Earth's atmosphere and get burnt out, but till then, they possess danger to other space instruments. Due to increasing number of launches, there is a large amount of debris in space, due to which accidents have happened. For example, in February of 2009, one of the Russian satellites, Cosmos, collided with an American satellite, Iridium, and because of that collision, hundreds of pieces of those two satellites have caused a lot of problems for other spacecrafts. Additionally, some countries have done some experiments to try and demolish another satellite in space using a space missile. This causes much more debris and the situation worsens. Then there are other kind of unintended human actions, like dropping of a glove or dropping of some other material in space by humans living in the International Space Station or other such platforms. These also act like debris. Then there are some other companies which plan to provide satellite-based internet connection by launching 30,000 satellites. So we are going to add 30,000 more objects into space, which will cause space debris and also obstruct the astronomers from looking at the dark night sky objects. It is estimated that there are nearly 100 million debris in low Earth orbit traveling at speeds of up to 7 to 8 kilometers per second. This speed is sufficient for a relatively small piece of debris to damage an entire satellite or spacecraft, as you see in the image. The biggest challenge in space exploration is the vast distances between the celestial bodies. Even though the Moon is our closest neighbor, it took the Apollo spacecraft nearly 3 days to reach the lunar surface. In the context of human space travel, the further you go, more is the time required for food or emergency medical supplies to reach you. Even at the fastest speed, the fastest spacecraft ever built, NASA's Parker Solar Probe, made one of the closest approaches on February 25th, 2022, passing a little more than 10 million kilometers from its surface at a speed of 150 kilometers per second relative to the Sun. At this rate, it would take about 43 minutes for us to fly from Earth to the Moon. The fastest spacecraft so far, which we have been able to build, that is the Americans, which is the Parker spacecraft, is moving at something like 150 kilometers a second. But it is still a challenge to travel to increase the velocity in space. Another thing is, suppose we have to reach some other body, let's say Mars. We need to plan and begin our journey much ahead in such a way that the distance between Mars and Earth is the minimum. In spite of that, it may take us 6 to 8 months for us to reach there. The farthest any human object has traveled are the Voyager satellites. They have gone much beyond Pluto. That means we are in the Milky Way galaxy. And if it has the strength, it can proceed in the same way. It may even travel intergalactic. It took them nearly 35 years to leave the solar system. The problem here is to receive the signal back. If we have to send some signal and we have to receive it back, it would take, even at the speed of light, which is 3 lakh kilometers per second, even at that speed, one-way signal to the Voyager takes about 22 hours. And by the time the satellite receives and sends back a signal, it is well over 2 days. The nearest star to the Sun, Proxima Centauri, is nearly 4.2 light years away. And 1 light year, as you know, is roughly 9.46 trillion kilometers. So even at its current speed of about 17 kilometers a second, it will still take Voyager 1 nearly 73,000 years to reach Proxima Centauri. As is obvious, even with a leap in our current technologies, traveling to distant world in one human's lifetime is still a dream. Another challenge of long-distance travel is the technology required for in-space propulsion. Some experiments with compounds such as ammonium perchlorate as oxidizer and titanium-based propellants are being done to reduce this time to travel in space. Electric propulsion, ion propulsion, nuclear propulsion. These are some of the very promising candidates which can help us overcome the challenge of large distances. Another solution is to use gravity assist from other objects in space. Also called a gravitational slingshot, it is the use of gravity of an astronomical object, like a planet, to alter the path and speed of a spacecraft. typically to save propellant and reduce expenses. Gravity assistance can be used to accelerate a spacecraft or to change its path. The gravity assist maneuver was first used in 1959 when the Soviet probe Luna 3 photographed the far side of Earth's moon, and it was used by interplanetary probes from Mariner 10 onwards, including the very famous two Voyager probes flybys of Jupiter and Saturn. The next challenge is about navigation. Once we are in space, we need to know our location. The Global Positioning System GPS affects our daily lives profoundly. There are roughly 30 odd satellites located at 20,000 kilometer orbit which can be used to tell us globally the precise latitude, longitude, altitude, speed and time. While we use GPS on Earth, we do not yet have GPS for space, something like a universal positioning system. So currently, we use satellites to connect spacecrafts to ground stations. But in long distance traveling, it might be expensive and impractical to place communicating satellites throughout the way. The universal positioning system is like when we want to travel from Earth to Jupiter or Saturn, we have to guide the spacecraft in such a way that we should first know the precise position of the spacecraft, just like the GPS tells us. This amount of precision is required because a minor error in, let's say, the angle theta over a huge distance r will lead to a multiplicative error of r theta. The universal positioning system works something like the lighthouse when you are traveling at sea. There are some special stars which emit pulses of energy called pulsars. Pulsars emit large amount of radiation and are also rotating, just like a lighthouse in which you see light rotating at constant intervals. Therefore, pulsar positioning is used to create a spacecraft navigation system. Let us now discuss about the effects of space environment on astronauts. For Earth adapted humans, space flight is no fun ride. From the strong acceleration during liftoff to surviving in space and to re-entering Earth's atmosphere, there are many challenges to human health at every stage, some of which are detrimental. The study of the effects of space on the human body is called space physiology. Here we discuss some of the challenges in detail. Radiation is one of the major troubles for astronauts. Even though space is nearly empty, it is bombarded by radiation and cosmic rays from every direction. On Earth, the ozone layer protects us from harmful X-rays, ultraviolet and gamma rays. In space stations, we still do not have such an efficient barrier to completely protect our astronauts from high energy radiation. The radiation effect is very harmful because it can cause mutation of genes or of skin cells that can cause some diseases in the astronauts. It also affects food and plants, which can be a real danger for space travel. Materials technology becomes very important in such cases. Which is the best material to use that will act as a shield? Even electronic circuits get destroyed, so they have to be covered with some special sheets so they are able to withstand the radiation. When mutations happen in microbes due to radiation, this mutation can lead to infection breakouts. Hence, astronauts should have a strong immune system and undergo a period of quarantine before leaving and on re-entry. Here we see the crew of Apollo 11 in quarantine after returning to Earth from Moon, being visited by then President of the United States, Richard Nixon. 9.8 meter per second square is the gravity familiar to the human body for about 6 million years. Despite being at 90% of Earth's gravity, the people in the International Space Station still experience the feeling of weightlessness as objects above the Earth are in a constant state of free fall. This condition, in which people and objects appear to be weightless, is called microgravity. The microgravity experienced by astronauts causes problems like decreased bone density. The muscles may also become weak, affecting the day-to-day work of astronauts. Prolonged exposure to weightlessness result in muscle weakness and a reduction in bone density, thus affecting the mobility of an astronaut. On Earth, blood easily flows from the lower body and the heart works to push the blood up. In microgravity, blood fluids tend to migrate towards the head. The increased pressure in blood vessels, if unchecked, can cause conditions like blindness. On the other hand, the reduced work for the heart means the heart muscles will shrink in size with time, leading to cardiovascular diseases. To counteract this, astronauts regularly exercise and wear compression cuffs around their thighs to maintain blood circulation. Like probes in space, humans also need to adapt to 3D positioning. Reorientation to space entails relearning head-eye and hand-eye coordination, balance and locomotion. Around 80% of astronauts experience motion sickness in space, while their sensory organs adapt to the stimuli in space. Astronauts get trained to overcome this problem and so that they can go out of their vehicles and perform routine repair tasks, sometimes also called spacewalks. To live in space, one should adapt to a different lifestyle. The constant sunlight and absence of 24-hour day and night cycle in space disrupts our biological clock or the circadian rhythm, resulting in stress and sleep loss. The distance from Earth and limitations of payload weight affect what astronauts can eat. Growing enough food for the astronaut inside places like the ISS is not possible, and cooking in space is very hazardous. Hence, food is processed in certain forms while ensuring a balanced diet. All this means astronauts should be trained for a whole new lifestyle. People with differential abilities have adapted themselves to accommodate their disorders. And some scientists believe that this adaptation can be advantageous for space travel. For example, the weightlessness could be a relief for people with mobility disorders. In 2007, the renowned astrophysicist Stephen Hawking traveled on a zero-G flight. Hawking later recollected it as the true freedom. I was Superman for those few minutes. The isolation from human civilization and the heavy workload of an astronaut makes them prone to psychological distress. The emotional state of individual astronauts can affect the whole team and the success of a mission. To mitigate this, space missions are designed to have recreational tasks like journaling, gardening, talking to their loved ones, etc. Above all, sound sleep is essential for orderly functioning of the brain. As we learned earlier, this could be very difficult in space. By using technologies like visual reality, VR, calming environments can be generated to help them relax. Here is a picture of NASA astronaut Catherine Coleman playing a flute on board the ISS in 2011. The farthest human settlement has been away from Earth's surface is the ISS, where astronauts live for a period of 6 months. Having permanent bases on distant objects like Mars would mean living millions of kilometers away from the Earth for long durations. Therefore, the payload has to be well planned to meet all the requirements of the astronaut during the mission. At such distances, if there are any medical or other emergencies, resupply or rescue missions would be impractical. A solution to this is the human base have to be self-sustaining and evacuation protocols at any stage uh, of the mission. ISRO's Human Spaceflight Center recently performed a crew module atmospheric re-entry experiment and a pad abort test for the Gaganyaan mission. With these challenges, we also see there are other opportunities for future space scientists and engineers to transform humanity into a spacefaring civilization. Fields like space architecture are ripe with opportunities for the youth as more and more agencies are looking to form bases in Moon and Mars. On Earth, we have systems and structures like large scale farms, transportation systems, water and electricity lines, residential areas, manufacturing complex, etc., that make life on this habitable planet possible. When we think of the hostile environment like space and other celestial bodies, we need extreme solutions. Space architecture in the theory and practice is the theory and practice of designing and building self-sustaining habitable environments in outer space. This is a relatively new and fast growing field as many public and private space agencies plan their bases on them. As a start, agencies are creating space analog environments here on Earth. Such missions can help us understand different components of space life. An adjacent field is space farming. As mentioned earlier, there are various limitations in carrying food into space. The more sustainable solution would be to grow food in space. Growing plants in a space station is different from growing them in a base. The former entails bringing all the resources to the station to cultivate plants. The latter involves only using the existing resources like soil and genetically modifying the plants to be compatible. This in turn demands more space exploration missions. The International Space Station routinely conducts experiments to study growing plants in space. The discovery of water molecules on Moon by Chandrayaan 1 has raised our hopes of finding harnessable water on Moon to supply future bases. Thus, we need a futuristic vision to help us find ways in which humans could lead a life in space and push our technology to great bounds to make it possible. We need imaginative power to rethink what would home look like even in hostile environments of space, moon, and exoplanets. Thank you.